We gotta review it real quick. If you know, here's what we're gonna do. I'm gonna go through these things. Anything you don't see, just sort of a review. Go and just yell at me and I'll stop and start explaining as best I can. Go ahead. So let's start with 1-4.1. I feel.
That's point two.
I know, but I'm gonna real quick.
All right. 4.1. A box contains 50 diodes, which 10 are going to be bad. A diode is selected at random. What's the probability that it is bad?
40 good. All right. This is straightforward. All right. We got 50 diodes total. 40 good, 10 bad. If one's selected from there, the likelihood that it's good or bad. Good.
What's the probability that it's bad?
Oh, bad. All right. So it's really what they call relative frequency. How often the event occurs in this event space. And you take that and just divide it into total outcomes possible event. So it would be for part A, at least in this one, the actual probability of, I'll call it bad, is just going to be 10 over 50 or 1/5. We did that already. Go ahead. What's it? Real quick, just go through.
If the first diode drawn from the box was good, what's the probability that a second diode drawn will be good?
All right. And this is really the second diode, but how would I do that? Just think about what happened. First diode good, right?
Yeah.
Class, anybody. What happens to this number if one was taken and it's good?
The total was subtracted by 1 and
There's 49, right. We still have 10 bad, right? And now we have 39 good. Y'all follow me on this? Just making a point. So therefore the probability of a good one or bad?
Of the next one will be good.
All right, what do we do here? This is now the actual, I call it the space of all possible values, right? So what is it? 39 over 40. It's that quick, right? This should be that quick for you. Y'all see this, everyone? How many understand this? I'm just asking because I get a lot of like stares. What are you good? Are you with me on this? This is not meant to be in any way. Yeah.
Would it be 39 over 49?
49. Pardon. Sorry. That's what I got you. Y'all, everybody understand that? It's just simple. This is as simple as it gets. And we're assuming that the likelihood selecting one is the same in all cases. There's not a skewed weight on it. Go ahead.
2 diodes are drawn from the box. What's the probability that they're both good?
All right. So one, I was trying to get at something else. They're both good, right? All right. So for the first one to be good, this would be the probability that 2 are good. And really what this is going to be is first is the probability that I select one good one. And then after that, the probability that I select another good one. After I select the first, so there's a reduction in number. You'll take a moment. This is the thing that I was trying to get at something else and I shouldn't. Everybody with me on this? Okay. And by the way, these events, I'm going to use this word now and I'll explain it later, are mutually exclusive. The first one gives an outcome. It says it's good. I mean, we're going to assume it's good. And this is good. Better hold off on this before I spend too much time in doing this. Anyway, for this, it's going to be a multiplicative probability. You all follow me? So the probability the first event occurred is going to be really 10, is good. So that's going to be 40 over 50. And then the probability that the next one is good is what we just did would be 39 over 40. And that's that number like 250 something over something.
156 over 255.
156 over 250. But is that it for that one, right? Now, next problem.
Telephone switching center survey indicates that 1 of 4 calls is a business call, while 1/10 of business calls are a long distance, and 1/20 non-business calls call.
Okay, so this is 1-4 point here. Now, here we're drawing a Venn diagram or something representative of what's going on. Really helps. Are you with me, class? I'm going to try this one. If you didn't, just be honest with me, things go well. If you didn't take a look at it and try it, please do, because these things tend to help you see, you develop a thought pattern of how to deal with problems that get much more complex. So first, we've got all calls possible, and I'm just gonna call that S. Everybody follow me on this? This is the way that, this is the event space, you might say, or all possible outcomes. Then they say, was it 3/4 or local?
One in four calls is a business call.
Or I'm sorry, business. All right, so that means we've got 1/4 here, and these are business. And that means 3/4 over here are non-business. Go ahead.
1/10 of business calls are long distance.
Okay, now this is the part you pay attention to if you haven't thought of it. For all the business calls, 1/10 of these calls are going to be long distance. Isn't that right? All right, so what is 1/10 of 1/4? 1/40th. You follow me? Try to get this down in terms of all of S. So that means here I have 1/40th, and these are going to be long distance. I'm just using LD there. Pick a moment, make sure you see what I'm up to. I'm trying to show you, in terms of proportions of S, of all calls, how this actually can be viewed and looked at and this isn't, a circular Venn diagrams, y'all follow. So, go ahead.
1/20th of non-business calls are long distance.
All right, so how much does that make down here for long distance, non-business calls? Well, 1/20th?
1/20.
All right, we have 3/4 of all the calls are in this, they're local, right? Or non-business, pardon, non-business. And of that, 1/20th is going to be long distance. So that means it's what, 30 divided by 4 times 20, correct, class? Y'all with me on this? Think about it. So that's going to be what? 3/80ths. Do y'all follow me? Here we got long distance, non-business, long distance business, and the rest is as it's broken up. With me? Okay, now one. It's a good one.
What's the probability that the next call will be a non-business long distance call?
All right, so for this one, probability of the next call be a non-business long distance call, right?
Yep.
Right. So if you look at this, non-business long distance, 3/80ths. Do you follow me on this, class? Just by viewing it. So this should be at least 3/8. I hope it's one of the answers. Because of this one. 3/80ths. And hold on. All right. Part B.
What's the probability that the next call will be a business call given that it is a long distance call?
Oh, okay. Now, here we could get into the. This is one way to do it. Remember, if we take probability of A given B is equal to the probability of A, and it would be intersect B over the probability of B. Do y'all remember me showing this on the Venn diagram? Just show hands. How many do? So I know what I'm talking. And if you don't, just level with me. I'm not going to yell at you. You're paying for this course. The only thing I'm trying to do is help you see this stuff and understand it. Okay, now that is the method that is the formal way to do it. Now we have to take a look at, since it says it's a business call, right?
What's the probability? Yeah, what's the probability that the next call will be a business call? Given that it's a long distance call.
Okay. So here's all the long distance calls. Y'all with me? That would be B. Follow me on this, everyone. With me? So this space down here, this is really the probability of B. And just for the record, what is it?
5/80ths.
You're going to add this and this, right? Isn't that what you just did? So this is going to be 2/80ths, that's 3/80ths, or this whole thing right here is going to be 5 divided by 80 in terms of proportional. We're just saying the whole area. Y'all with me? And that represents calls, total calls. So then it says what? Now they want the intersection of, of what?
What's the of a business call? What's probably the next call will be a business call.
That's this, right? That's business and long distance. That's the intersection part right here. That's what I was trying to really drive home. I did it. Okay. So this is really going to be probability of A intersect B. Just trying to bring it back to the Venn diagram. So y'all agree with this? And what is that going to be? So that's going to be, what is that, 1/40th, right? Over 1/40th plus 3/80ths, right? And multiply everything by 80, you get 2 plus 3, or 2/5. Do you agree with this class? Oh, is there anything else? Is this the way you tried?
Yeah, kind of. I didn't get it, but yeah.
I mean, you have to do it in terms. Just think back to the actual that method, and it really you have to always take. I think about these things. I don't always use the language the book does. My area is radar. Most of the stuff that we deal with through friend or foe identification, the confidence level in something being one or the other. But for this, as soon as they give you some details where you can eliminate the rest of the problem, then you start looking at the actual possible outcomes in the event space that you're in. And I use that word event space. Then it's really a ratio. It's just a relative frequency. Okay, so part 3.
There's
What is it?
what's the probability that the next call will be a non-business call given the previous call was long distance?
All right, now I want you to just think.
Is that a red herring thing?
That's one of those things, just making sure you're thinking. What is the probability that the next call is what?
Non-business call.
Given,
Previous call was long distance.
does the previous call have anything to do with the next call? So what is it?
3/4.
Do y'all see this class? I don't know if that's the right answer, or that's the answer. By the way, some of these answers I found out are not right. I'm going to say this: people make mistakes, but they're not right. Those have answers. There's solutions I posted for the actual problems to get to. All right, so are you with me on this one? I want to keep going on this stuff. Did you have other questions?
No.
I'm going to work through these examples. We can work some problems, and these problems will get progressively more difficult. And you have to understand like the basic concepts to this. Now, I know other professors, they'll spend a lot of time developing theory for this type of course. If you take it in the math department, especially application makes it real. You can understand it. Okay, I got that one. Now, 1.51, how many tried that? If you didn't, it's okay, but you tried it. Did you have any problems with the first one? This is what? A Venn diagram problem. Do you have it there?
Can be.
1-5-1. And I'm going to draw this, but I need to talk about it. And I'll tell you why, because it's, this is the way I am too. If I start reading these things and they're too simple, I almost go to sleep and don't pay attention. I mean that too. But you have to almost force yourself to be attentive to the small details in the beginning so you can carry that principle forward when it gets much more complex. Go ahead. What's the answer?
A intersect B, union A minus B.
All right. So for part A, this is strictly something that's theoretical. It has nothing to do with diodes or anything like that. And he says he just wants what the value is of, I think that's it, of A, go ahead and say it.
A intersect B, union.
Intersects?
Mm-hmm.
Okay. Union
A minus B.
All right, now, something I didn't cover was minus. I want to be careful with this because you're engineers, you're inclined to subtract mathematically things. Follow me on this? Like if set A was numbers 1, 5, 9, and set B was numbers 2, 3, 4. For some reason, people will take the first set and subtract the second set and get negative values. Do y'all follow me? Now, there's one thing I didn't say in the first class I wish I would have. Probability can never be negative. It can be zero, but it can never be negative. Do you follow me on this? And the areas related to probability have to be positive. The lowest they get is called a null set where it can't happen. They can't be negative. You can't have something associated with a negative chance of it happening. That's as simple as it gets. Okay. Now, when you look at this, probably the first thing I'm going to say when you take A minus B, and I want to explain this as best I can. It means you take all of A and anything that is B that is in A, you remove it. All right. If there are other elements in B, you don't make them negative. Do y'all follow me on this? So that would mean if I take a look at A minus B, what we're really looking at is something like this. It would be A minus. Y'all would. All right, now that would be the area of this. You agree? Then it says A intersect B. Well, A intersect B is this, right? And you'll notice there's a union. So this would be A intersect B. Agree, class? Can y'all all follow me why I'm doing what I'm doing? Well, what is that? Isn't that A?
Mhm.
How many can see it? This is just to make sure you can see these kind of things in the Venn diagrams. Now, that particular problem is kind of ironic, but you're going to see when we actually start constructing solutions, you're going to need to do some stuff like this to be able to interpret or simplify. You with me? Part B.
Complement of A.
Oh, all right. A complement means everything in this set that is not A. Y'all, everybody with me on that? Matter of fact, what it would be is you could just take that B circle and erase it and just say everything outside A is what we're talking about, A complement. It has to be in the set of all possible outcomes or the experimental outcomes. Go ahead.
Intersects A minus B.
Is A minus B in parentheses?
It is.
All right. Now I want to take a look at what that's going to be. I want you to do it. I want you to just think about this. Tell me about it. Let me this. And I'm going to simplify this. Well, so when I look at A minus B, I'm going to put it this one. That's this right here. This would be A minus B. Then when I have A bar, now this is important, A bar, right? So here it's matching a line, right? That's all of A. A bar is everything outside here, and trying to draw this thing best I can. Correct, class? All right, so I have A bar, everything outside, intersecting with A minus B, right? Isn't that, look at this. You got A bar, everything outside, and A minus B is this, right? And everything outside, what's the intersection? Or is there? How many see that there's no overlap at all? right? Everything inside here is A. Everything outside here is A bar, correct? There's no overlap. You all with me on this class? So it's zero. It should be the null set. You should have a zero there. Does it?
Yeah.
Okay. What's the third part?
A intersects B.
A intersect B. Go ahead.
Intersects B union A.
Intersect B union A.
Yes.
Okay. All right. How about this one? Give it a second to think about this, please. In class, is the best time to see or question. Here's the way I do these problems. I'll draw this separately outside that net. If you take a look at that, A intersect B is what? If this is the S, it's this. Got it here. This is A intersect B. Do you agree with that? Now, where's this? B union A. A and B, correct? Can you all see that? So it would be it's basically going to be it's not drawn very well, but I think you get me. It's all in that. And they want the intersection. How many C's just A intersect B? Can you see that? But if you don't draw these things, I'm going to tell you, just playing around your mind, you can make mistakes. Is that the answer? All right. That's not a bad Venn diagram problem in true abstract sense. But here's where it gets complicated. When you bring a third set, a C in there that has overlap. Y'all with me? We're going to see this in a bit. Then you have to be very clearly thinking about what, in fact, would be the final areas we're going to be talking about. I want to make sure. Can you read all the stuff I put up there, the PDFs and all that? I mean, both solutions and the exercises of the book. There's problems at the end of each chapter. Okay. Next thing.
I brought one of the erasers from upstairs, by the way.
I hope it works. Sometimes wet cloth is better. They actually have this. That stuff is either is Windex or one of these window cleaners that they use. Thank you very much for doing that. I have to clean the erasers. They do get dirty. All right, next. Okay. 1-6.1. I gave that to you, didn't I?
Yeah.
All right, this is one that has wrong answers. How many tried? Just learn that. This is you know what a roulette wheel is? How many do? I'm assuming everybody does. Now, you gotta just, if you don't, tell me. If you don't know what roulette or poker cards are, or whatever dies, and they'll probably have other things. Let me know because, I make that assumption. They don't have roulette, certain countries. They have other things. So they have to be careful. But most people. So you got a roulette. Now, a roulette wheel basically is something that they spin, they throw a marble in it. And it's going to have all these slots. They're going to have slots where they're going to have 37 total slots. One of the slots is actually green. And that's blocked. I mean, it's basically you can't bet on it, I think. I don't play with it. With me on this? And then there's going to be 36 total slots outside there. I'm using the word slots. They're places where a marble could land. What they do is spin the thing. I think everybody knows this. The thing goes flying around and lands in one of these things. It's just trying to make it random. It's a random. So there's 37 total slots or outcomes possible. 37 total. And then one of them is green. Then there's going to be, let's see, 18 black. Wait a second. We're going to have, I think it's 18 black, 18 red. But I think you know what it is. You can Google a picture of roulette. And now the first part of the question.
Find the probability of A and the probability of earning $1 bet on this number.
Say probability of A is what? What is A?
Let event A be the occurrence of the number 1 when a wheel is spun, and event B be the occurrence of the number 2.
Now this is the relative frequency approach. These are numbered. So there's slots. I didn't say this. There's 1, 2, 3, 4, 5, all the way up to 36. The 37th one is great. With me. So the probability of any one of those occurring, assuming it's a level thing, in other words, a fair roulette wheel. Either one of these is going to be, well, you got 1 out of 37. 1 out of 37. Y'all with me? And that should be right. And it is right. I looked at this problem because I was messing with this. There's a wrong answer. Now, what he asks for, does he say expected return on a dollar bet?
Probable return on a dollar bet.
All right, I'm going to use the word expected. So if you bet $1, what do you expect to get in return in the long run? This experiment went on forever. Bet $1, bet $1, bet $1, bet $1. On average, what you return? Follow the thoughts on this one? So how do you do it? Well, so the actual return on a $1 bet would be, first you take the probability of the marble landing in the slot you bet on. Bet $1. So that probability is 1 over 37. And then you multiply that. Yes.
Sorry, I don't mean to interrupt, but there's actually the 0 and the double 0, so it's 1 out of 38.
Is there?
This one doesn't have a double
Oh,
zero.
it doesn't? Okay.
That's the problem I've got with some of these problems. I don't play roulette.
Okay.
I've never played. I'm just assuming what he's saying is true, but he's using 37 as the total possible outcomes.
Okay. Sorry, I didn't look at it. So.
If it's 38, then we can alter it. That's a great problem. I do it. Just change a few things, see how people do with it. Anyway, with this one, there's possible 37 outcomes, right? But the thing pays off as 35 to 1. Now think about it. If it paid off 37 to 1, in the long run, you get back your dough. Do y'all follow me? If it paid off at a rate of 37 to 1, but it pays off 35 to 1, right? So here, bet $1. What's the payoff? 5. Hit it, it's going to be 35. Oh, with me? 5. If it doesn't hit that number, you lose it all. Got me on that one? So now it's minus. This is an interesting problem. It's going to be minus. Well, the probability of you not winning is going to be 36 over 37, right? Y'all follow me? And what? You're going to lose $1 if that happens. Just minus what? We'll assume this is in terms of dollars. Do you agree with this, class? I want to make sure you see the logic, because he wants the expected return. I like the word expected return. If I bet $1, what can I expect to get back? As engineers, you're going to find out in the real world, you always want your expected return on something. Like how, in the long run, if the thing went on forever, billions and billions of times, what would the average value of the money you get be per roll? And in this one, what do you notice happens? It's going to be a minus 1 over 37, which is about minus 2.7 cents. Did anybody check that out? Now, the book doesn't have it, but that's the right answer. Can you follow me in the logic? If you're just looking at, if you bet $1, what you would get back. Now, listen, if you bet $1, has nothing to do that you bet $1. Then it would be 35 over 37. That's one of the answers, I believe.
It's not fair.
Okay. Well, see this. Y'all follow me on this one, class? Now, I'm talking about the expected return. If I bet $1, what can I expect to get back on that dollar? Well, I actually am going to lose 2.7 cents every time I spend on average. And anybody who plays roulette wheel, if it's a fair roulette wheel, thinks they're going to win money in the long run. They can't. If they bet all the money that they have on one spin and they win, believe it or not, there's about a 46% chance you're going to win. And you can, you're basically going to get your money. You're going to make money at whatever the payoff rate is. But the probability of that happening, the expected value is the highest with one roll where you bet it all. As you dice up your money, say you got $1,000 and you bet $1 bets, spin it, the likelihood of making anything after like 1,000, it goes to 10 to the minus 47th. I did this problem yesterday. I was looking at it and I'm thinking, well, that's a very dumb game. People are good at math.
And the fact that they'll be like, here's the previous rolls. The previous rolls has nothing to do with.
Or nothing except the current roll, and the statistics never change. Now I don't know about the double zero tips, but I do know one other thing about Las Vegas or any place where gambling is. On average, the house always wins, with one exception, and that's blackjack. And have you ever heard of a book called Bringing Down a House? Have you or not?
I think I've heard of like people like trying to count cards.
Okay, let me tell you what happens. This is true. There's a movie in this, and I was teaching this a long time ago. I don't normally teach this. So a guy from, I believe it was MIT, you can look this up. It's called Bringing Down a House. Professor in there has a bunch of students and they're all very bright and they have great memories. And they go into the casinos. Now with blackjack, they play 5 decks. And they don't, basically they shuffle them, but then they keep using the deck without reshuffling every time. 5 of them, think about that. So they do it. When you get down to the end, mentally, one kid keeps note of how many jacks, the other, or face cards. They came up with a scheme where they knew exactly how many what cards have been played, what cards remain. They came up with a way to do it. Now, if you know you're getting down to the end, and there's the thing where you want the highest expected return on your investment, you start betting more and more if the hand they deal you, say you get a jack and a jack, 2 jacks or jack king, and you know all the aces basically are out. Maybe there's one left. Now you bet on the sky on that, the legal limit of the house. But they came up with a scheme so they could count and bet and win. And I think they had all these disguises. So they could go into one casino and now they're not all like right next to each other. They're on purpose staggered, but they won a fortune. And that was one of the few times Vegas got stung by something. Are you looking it up now? You should take a look at that. You want to see about how clever kids can take down a gamble. I mean, look, Las Vegas, you're not going to take anything out of there on average. They win all the time. So don't. The moral of the story is if you've ever done these things, unless you've got incredible memory and you play blackjack, you're probably going to win this game. That should be the answer, but it's not. That's for part A. What's part B?
Find the probability of A union B and the probable return on $1 bet on A union B.
Okay, now for this one, unless I miss what he said, we have 37 possible outcomes. There's something in there that a bet, if you bet 2 adjacent numbers, the payoff is it's going to be 17 to 1.
Yep.
Follow me on this, class? So now, if you're going to do that, this is a $1 bet, so I guess 50 cents here, 50 cents here. If you assume it's actually $2, you're putting it's a different outcome. Go with me on we're going to make it 50 cents on each, a total dollar spent. So now the probability of these 2 numbers that are going to be, that may happen, what do they call it, adjacent to each other. That's really going to be, that's going to be 1 over 37, and then 1 over 36. And then you have to take a look. Actually, no, I did that wrong. So Does it say two numbers adjacent?
Yeah, it says
Because this is a problem.
A and B are 1 and 2. So they are adjacent.
All right, now we're going to change the dynamic. They have to be adjacent, right? You can't have a 1 and a 3 or 1 and a 5. You with me on this, class? But the way that's a much different problem. The way he structured this is he wants you to think instead of having 36 possible outcomes, you're going to have 18 possible outcomes. Think about this. He's saying we're just going to look at these things as blocks instead of we'll see this in the future when you get all the permutations. But I think that's what he meant, because otherwise the answer he has, it's first the problem becomes much more complicated. If you think of all possibilities, you could bet on a 1 and a 2, right? But then the ball could land on a 1 and a 3, or there could be 1, 2, and all the way around there. They're not adjacent. And this is something I'm not explaining very well, but it gets much more complicated. But if we assume that basically instead of 18, or I'm sorry, instead of 36 possibles, you got 18 possible outcomes, then the probability of winning would be 1 over 18. And the return would be 17. If you got that. I'm just trying to, I'm not saying it the way I want to because I'm thinking about all the other complexities in this problem. But just think the event space here is going to be, or the outcomes are going to be reduced. Now, that's true, but there's something else in there, that blank, that green one, that you have to account for. With me on this? And this would be multiplied by $1. Right? Then you would subtract, and the likelihood of not winning. It's actually a 17 plus 1. So this should be 18. No, it's 17. Second. Oh, this is still going to be 36 over 37. And for this one, and it's going to be a minus because the dollar's better. I'm not saying this exactly the way I want, but for this particular problem, the likelihood is actually not 1/18 because you have that green one. It should actually be 1/19. And then the answer is going to be totally out of anything he has in the book. Let me just say this about this problem. Thinking about now. Don't worry about this part because we have to look at something down the line about all possible outcomes. What was the final part of that one?
Finding the probable return of a 1 element bet.
For that?
And you know what the answer was?
Well, it won't have the answers in order. You're out of order.
Oh, what are you asking?
I was asking, is there a part C?
Oh, no, that was it.
Okay. We'll come back to that one. I was messing with that, and I realized just now that the second problem is a much different problem because they have to be adjacent. It's not betting on two numbers, it's adjacent. So now that space is much more constrained. And that, I believe, causes a big problem. We'll get back to this one. I want to keep going on this. I did something on that one to be sure. And we're going to do switch things, but these classic problems are gambling problems. There's books written on them. Some of them they go into the finest minute detail about this. And there used to be a thing on, I don't know if it was online, but books written how to beat, it would be either poker, blackjack, roulette. All right, and they literally they sell these things. And it was all based on flawed theories. Okay, I gotta get those switches. But I wanted to do 1.6 or 1-6.2 for one reason. This is the kind of problem I'll probably ask something related to it from Friday's quiz. So for this one, you can want to tell me what it is.
Draw a Venn diagram showing three subsets that are not mutually exclusive.
Hold on 1 second. So this is a set of all possible outcomes. Here's my A, here's my B, and here's my C. And what do they want?
Using this diagram, derive an expression for the probability of A union B union C.
Probability of A union B union C. Now this is a good one. I want you to see this and then think through it with me. I'm not going to make it more complicated than this. If I put a D on there, it would take too long. First, I just want you to see what we're really talking about is we have to find a way of talking about the area in this clover right there, everything inside. You with me? Take a look. So what I'm going to do with this, I'm going to simply add up the areas of A, B, and C for stars. There's a lot of overlap. All right, so I'm going to say what this is going to be is the probability of A plus the probability of B plus the probability of C. Now, what I've done is I've got overlapped areas I have to account for and get rid of. Y'all with me, class? I have to subtract it off. With me? So then I'm going to subtract off this area first. Just go with me on this one. With me? So I'm going to say subtract off probability of, and that would be A union B, or I mean intersect B. A intersect B minus the probability of B intersect C minus the probability of A intersect C. Now, remember, because I counted these areas twice. Y'all with me on this? So I subtracted those areas off, but I did one other thing too. See this area right here? That's the intersection of A, B, and C. Can you all see this? Now I've subtracted that how many times? Well, here I subtracted it, right? So it accounts for one. Here I subtracted, or basically I subtracted this, and subtracted this, right? I only want to get rid of that. Try to say this in a way. All right, let me say this. If I've done that, right, because there's overlap here, here, and here, I have to add back something. Can you all see that, class? Are you with me on this? Can you see it?
Yeah. So, when you're subtracting that, you subtract out the middle 3 times.
Not the middle. See, here's A. Like, if you take it back a second, just a second. Suppose we just have A and B. You'll see this. Here's the overlapping area, right? So just if we talk about area, A union B would be equal to really A, right, plus B minus A, intersect B. Can y'all, you with me on that? All right, now, add a little complexity. What if I have this here as C? Well, the way they'll tell you to do it in other books is now do this problem. You do AC first. You're going to get basically this type of. But here's the problem. If I I could keep on adding, so it'd be plus C, right? And if I do that, then I have to subtract out A union C. Just take a moment, see if you can see that. I draw it too long. How about if I draw it bigger and we'll talk about it over here? But I think you can see it here. If you're just talking about, in some way, mathematically defining the total area that A, B, and C cover. I mean, and basically there's overlap, right? If you start with A, B, and C for now. Now, because you've accounted for this area twice, you subtract it once. That makes sense? Then you have to subtract this area once, right? But now I've subtracted that center area more than once. Do you follow me? This A intersect B intersects. And then you have to subtract off this area. With me? So I have to add something back in because I've subtracted that middle one. What do I add back in?
The
I don't know how I
intersect of
pardon me?
the intersect of A and B intersect C.
A intersect B intersect C. And if you look at this, that's fine. When I do this, now I've carved out that center one. And so I believe it's going to be 2 times that if you look.
It only has it once.
Wait a second. Let me see here. Did I do something wrong?
The logic makes sense. I would think it would also be times 2 of the middle to where because what you're subtracting it 3 times, well, then you add it back twice, so that makes it look like you only subtracted once.
The minute I subtract this and this and this, right? What I need to do is if I subtract this once, I'm subtract that from, I've accounted for that middle area. Now when I subtract this, right? Now there's a deficit because that's taken out twice. Then when I subtract this, I mean, 1 times 5, but this and this one would make it a 2 there. You'd have to add in. You really want to, I haven't done this problem, but I've found this out. If you just take a snippet of that problem statement and put it into Claude or ChatGPT, 99% of the time it gets the right answer. It does. I think that's an error, but I'll check. It should be, this should be twice here. And it should make sense. You really want to know how to do these things, Boston? I think you know what I'm about to do. And I'm trying to show you 3 identical rectangles. So I'm trying to show you. Each one of these has width of 1. It's easier to see this way up. And this is 1, and this is 1. Now, have this come over exactly 1/2. It's 1/2 there, and this would be 1/2. And we've done it. Trying to move that one up. Now this is 1/2. Now, what I'm really trying to do is make it something easy to see. You do the add, addition, or subtraction. So if I add the areas of each one of these things, call it A, B, and C, it's 1 plus 1 plus 1. With me, class? Remember, the dimension of this is 1/2 by 1/2. So if I take this, and I want the total area that is in this rectangular thing. It's going to be 1 plus 1 plus 1. Then from that, I have to subtract off overlapping area here, which is going to be minus 1/2 times 1. And then the overlapping area here, and if you look at that, that's going to be minus 1/2. And then the overlapping area there, which is minus 1/2. Then I have to add this part here to it, and that's 1/2 by 1/2. Can you follow me on this? And you're going to do that 2 times, then you should get the right value for that. Because what it should be is this is going to be 1/2, 1/2, 1, 1/2, 1/2. When you do this, you're going to find out that that will come out right. So that's really 1 minus 1 gets rid of that. And
Is that middle section 1/4 by 1/4? Or is it 1/2 by 1/2?
no, actually, this should be 1. This should be 1/4 of the side. But it should be multiplied by 2. But if you play around with that, you'll see this stuff right here. It's hard for me to draw this exactly. But you with me on this class? Believe that's wrong. But I'll check. You done. All right. That's that one. Now, I wanted to take care of one thing. The first couple of classes, I do a lot of problems. But I did want to talk about switch problem that I gave you last time. Um, I was going to do Independence Day, but I'm going to wait until Friday to do that. I want to just talk about the switch problem. I'll give you some more homework problems that are going to be related to everything we've been covering. Working problems. Do you all remember that switch thing I put on at the end of the day before you left? I don't know. Some people may not. I want to tell you these problems are very pertinent to what you guys will see in the real world. They have this kind of stuff, and you're always trying to figure out will it work or won't it work. So when we did the switch problem before, I mentioned that anytime you have things in series, you have the probability of it working like this. They always do this. So say this probability of being closed is P1, the probability of being closed is P2, probability of being closed is P3. They want to know what is the probability of this relay work. These are all probability of it being on or functioning properly, right? Now, if they're in series, they're also something where they're independent. This switch does not matter what happens with this switch. This switch doesn't matter what happens with this switch. And basically, they're all independent. You with me, class? So if that's the case, the probability of this thing working, remember, these probabilities are the working, right? The total probability would just be a P total for this one. It would just be P1 times P2 times P3. You can extend this indefinitely series. And what that means is I can take all these switches and replace them by a single switch. It looks like this. And just call it P total. Just like with resistors and series. You follow me, class? Only you don't add them, you multiply. Now, if you have switches in parallel, like so, And I'm gonna put 3. And what we're trying to do is find out if there's going to be a connecting path between the input and output. In other words, what are the chances that this thing's working or not working? All 3 of them, right? Well, this one you can think through it, you can see it. If any one of these switches works, it works. They're in parallel, it doesn't matter. It has nothing to do with which one it is. What you want is the probability of this thing not working. You follow me? With me on this one? Just listen. So the probability of it not working, this one, is going to be 1 minus P1. The total probability has to be 1. This one not working is 1 minus P2. And this one not working is 1 minus P3. Y'all agree with that, class? All right. So what I need is the probability that all of them work. And y'all see they're independent. This doesn't matter on this one, doesn't matter on this one. You all with me, class? Because they're independent, it's like that. Only now you're going to take the probability they're not working because you need the probability of none of them. So the probability of none working, no, or not working is just going to be 1 minus P1, 1 minus P2, 1 minus P3. So that's the probability of it not working. Therefore, the probability of it working and this is for this one, is simply going to be 1 minus the probability of it not working. Y'all agree with that, class? Now I want to just finish up. Give me an extra minute. I want to show you because I'll tell you right now. I'm going to ask something about these switches and I'll give you some more homework on the quiz. Everybody got that? 2, 4, 6, 8, 9, 10. We're missing people. Did y'all realize there was 14, I think, registered the night before? I don't know where they are, but I think. Wait, the guy who's recording, you got it with this? Okay, good. Thank you very much. By the way, I was sideways.
Oh yeah.
Anybody else look at that recording? Not yet. Well, did you notice it on the first recording?
I guess it's because I was.
You had the camera, or you had that shifted, but you can just straighten it.
That's weird because on my computer it did it. I don't know. Strange. Maybe I looked at it on my phone. I don't know.
Anyway, doesn't matter. So getting back to the kind of problem I want to talk about. They have a problem, and I gave this to you. I don't know if you actually looked at it. I'm going to make it a little bit more challenging. So call this P1. This is probability of working P2, P3, and P4. And I want the probability that basically there's going to be connectivity here. These are all probability of working. How would you do the problem? I think you're going to reduce it. Just think about it for a second. I know I'm going to be over by a minute. I want you to think.
And we're solving for them working, right?
Yes, working. From here, input to out. In other words, the conducting path.
Would combine 2 and 3 first.
Absolutely. And what would you replace? You're right.
Just them multiplied together.
P1 or P2 times P3. Absolutely right. I know I'm out of time, so I'm going to just do this. You're absolutely right. You're going to take it and make a switch here.
You
And
got 15 minutes.
what?
You got 15 minutes.
Isn't it over at like 11?
It's 11. Yeah. You're good.
I don't know why I'm thinking 9:30, 10:45. That's just always been the summer spot. Now till 11. Anyway, if we look at this one, this is going to be P2, right? Times P3, correct, class? All right, now keep going. Everybody with me on this? This isn't that bad. Somebody else.
You do 1 minus P2 times P3 times 1 minus P4.
Well, yeah, first let's put in probability of these two because they're parallel, not one. So this would be 1 minus P2 P3, and this would be 1 minus P4, right? Just take a moment with me. Okay, they're in parallel. Now I want the probability that this segment isn't working. What do I do?
Not working would be 1 minus P2, P3 times 1 minus P4.
Right. So if I have 1 minus P2 P3, then I'm going to multiply that by 1 minus P4. That's the probability of that not working, right? The probability of it working would be 1 minus that, correct? Now I have the probability of that working. Now I can replace that with that value there, and I'm just going to call this P2, 3, 4. So I can replace it with a switch as P2, 3, and 4 of working, and then I have P1. I think by now C would have different. P1 here. And now I need to find the probability of that switch working, which is
P1 times P2.
it's really this times this. So it's going to be P1 times P2, P3, or I should say P2, 3, 4. That's a subscript, and it's indicating that. It's going to be that, and this would be P of this system working. Do you agree with this, class? It looked obvious when somebody does it. When you start doing it, it gets a little crazy. Now let me show you the next situation that logically comes up. This one, maybe throwing you because it's not just series and parallel. I alluded to it last time, but I didn't give you the right answer. So I didn't write this. So if you have, okay, switch here, call it P1. Then I want to take switch here, switch here, switch here, switch here, straight, and finally this one. This is the month. And I want the probability of this working. I think you can see, you don't want us to bug it, right? So, anybody got any thoughts about how you do it? I want you to just listen to me carefully about this. Well, here's what I can say. With me? Forget that middle switch, man. What if we have the probability of this one? Can you get it? I want you to listen to me. What would it be? If I take P3, P2, that's the probability of one switch up there. P, whatever that is, 4, P5 down there, right? Those are both in parallel, so 1 minus P2, P3 at the top would be not working. 1 minus P4, P5 at the bottom. multiply those together, and then take 1 minus that, you have the probability of that whole thing working without the middle one. Are you with me? Then you would have to multiply it by this to get the probability of that actually working, right? Without the middle link. The middle link. The middle link has a probability of being open 1 minus P6. Do you follow me? So the way you would do this problem is you're going to say, I'm going to find the value of the probability of this circuit first. Now, how many of you know how to get that? You pretty feel confident, right? Then you're going to take that times the probability that the middle switch is open. With me? Can you all follow? So then I'll call this circuit A. So I'm going to say the probability of it working is going to be equal to probability of A working times 1 minus, in the middle switch was P6, because that's the probability of it being open. Remember, I opened it, right? Then I have to add to this a new system. Now assume this switch is closed. Y'all follow? Y'all with me on this class? Well, now, if we want the probability that's closed, these two are parallel, these two are parallel. Y'all see that? Can you see it back there? I mean, I got to make sure everybody's on the same page. You with me? All right, now this one's 1 minus P3 times 1 minus P5. Take 1, subtract that, right? That would be the probability of this one working. Then 1 minus P2 times 1 minus P4. Take that quantity, subtract, we're going to take 1 minus that quantity. Now I have the probability of this one working. They would be in series. Add them up. I mean, not add them up, but take this probability times this probability of working plus this. That's the probability of this. We'll call this circuit B right here. So you would have to add to it the probability of B working, and it would be times 1 or times P6. That's the probability of a short being there. You follow the logic on this one? Now, here's the deal with these problems. You can see how these things could get bizarre and very complicated. Because suppose there's another switch, all right? A switch that does something like goes from here to here. Y'all with? You can get absurdly complicated stuff. But as long as you keep your head on straight and realize you can break the problem down to sub-problems, each of which have a probability of being there, you can solve these kind of problems. How many understand what I was getting at here? Make sure. You have questions about it?
Which one was the B working? Was that the short?
No, yes, that's this short. But what I was, and I'm going to tell you one thing. Anything like this, if you just take a snippet with your the snippet tool, you can paste that thing into what ChatGPT or Claude or any of those things, and it will give you almost guaranteed the right answer. Almost guaranteed. I say that hesitantly because one time, this happened in the last 4 or 5 months. I asked ChatGPT who the last American was to win the Australian Open, and gave me the wrong answer. Madison Keys, I think, won it last year, and not the previous Australian, but it gave me something else. So it does make mistakes, but it's mainly not on the problems like this. It'll make mistakes historically about not really a piece of data. But this stuff's pretty accurate. Have you ever tried this stuff with any of these problems? I'm assuming some of you have, but I could be wrong with you. Because that stuff is amazing for these kind of problems. You know why? Statistics, probability, ubiquitous. It's everywhere. Business, physics, math, engineering. Now, specific problems related to radar, it does sometimes get the wrong answer, but something just general problems like this, that's no problem. Okay. Now, so yeah. was gonna get into independence, and I'm gonna mention this in the beginning. This is not really deep thinking. I want you to know that when you talk about probability, one of the key things is being able to understand if one event is linked to another event anyway, because that causes some real problems if you don't see it. And I'll give you an example. Say you're rolling two dice. This is in the book. If you actually take time to read the text, it's in section, I think, 1A on independence. If you take two die, okay, basically throw some dice, all the possible outcomes would be from 1 through 12. And I think there's no question everybody's thinking this is just going to be dice. That's the possible outcomes if we add the numbers. Okay, it's like roll a 1 and then roll a 5, out will come with a 6. You with me, class? That's just reality. Now, if I talk about after rolling two dice, there's an outcome of 7 and an outcome of 12. This is where it gets kind of abstract, just follow me. And I ask you, are these events independent or not? Think about it. They were caused by rolling the same two dice. Follow me? If a 7 appears, it's one outcome. If a 12 appears, it's another outcome. A and B, doesn't matter how you designate this. Are they independent or not? The answer is no. If one occurs, the other cannot occur. Y'all with me? So it means that if one event occurs and the other cannot occur, they are not independent. They're dependent on each other. Given the fact, I'm just telling you the general idea. Now, a completely independent, and this makes sense to you. If the first event is drawing the likelihood of drawing an ace out of 52 cards, regular deck, and the second event is rolling a 3 on dice, you can plainly see that they are completely independent. The outcome of one has no bearing on the outcome of the other. Y'all with me on this, class? That's independence in a nutshell. The thing about this and probability, here's where it gets hairy. When you take a look at any two events that are mutually exclusive, try to draw this. When we think of like event A and event B here, the thing that is implied is they are impossible outcomes of a system or an experiment. Y'all with me? Now, when I talked about cards and drawing an ace and dice and rolling a 3 or whatever the number is, they're not in the same outcome space. Do you follow me on this, class? They're independent of each other totally. You with me? So this is kind of a drawing. The standard Venn diagram wouldn't represent what I'm talking to tell you. So now when you take a look at the probability of event A intersect B, this event space can't be used for it. Y'all with me on this, class? Because what we're taking a look is that they don't have the same possible outcomes in the space. If I'm drawing a card, I can't have a 3. Oh, well, I guess I could. I'm trying to say that the die outcome and the card outcome are totally separate. They don't occupy the same output space. I mean, they don't have any possibility of one being related to the other. So in that case, if there's independence, or if they're independent events, and I'll spend a lot more time on this, then the probability of A intersect B or both happening is just the probability of A plus the probability, times the probability of B. That's all it is, if they're independent. I'll tell you where this is in the chapter, so you can see this. And it gets a little hairy here, because how I do is draw a Venn diagram. And you can see there's no intersecting area there. It's because they're two separate sets of outcomes. This assumes in that set of outcomes, they occupy the same experiment. Let me give you the page number. This is important because it does get confusing.
It's 27.
Yeah, and by the way, I didn't give this to you, but the exercise is 1-8.1 and 1-8.2. I would do, and I'll give you some more. But if you look right there on page 27, let's see here, man. Yeah, in the first page, 27, 28, and then we'll get into the combining experiments on Friday. But they discuss this, and get yourself familiar with that because some of the stuff it gets confusing quick when they talk about that. Uh, I am over. I'll put some more homework up. If you have questions, just ask. Did you understand that? Even though that roulette wheel, in fact, I'm trying to explain this and I realize,
See, that's what I was wondering. Was like, oh, did he solve it with having two greens, but then he only put one green out? And it's question like, I'm wondering where he went wrong with it.
I don't even understand how he got 36. Because like I could see if it was 35 out of 37.
no, actually, with this,
Because
there's supposedly 18 black, 18 red. In a roulette wheel he's talking about. There's one that is green. All right, so that's 37 outcomes, possible outcomes. So the probability of landing on any outcome is 1/37. The numbered ones are from 1 to, I guess, 36, but I've never been at a roulette table. You tell me you got zeros and 11. So it's 1 to 36, right? But there's 37 slots. So when you take a look at the probability of landing on any one of those, it's 1/37. All possible. Follow me? Now, the payout, say you hit the one, remember the likelihood is 1/37. The payout is 35 to 1. So that would be how much you would gain. But you put $1 in. Now, what's the probability of losing or that being a negative thing? So it would be minus the one, and then it would be 36/36. You're always going to lose money. I mean, the expected outcome is negative.
I think so, yeah.
He didn't factor in